Hello, everyone, and welcome to the Human Survival Archive. Today, I'm honored to be joined by Dr. Jennifer Fogarty. Dr. Fogarty, it's a pleasure to meet you. Thank you so much for taking the time to join me today. To start, could you introduce yourself and tell us more about your background?
Well, thank you, Harsha. I very much appreciated the invitation to be here. Sure, I would love to. So, I began my education pursuing, medical research. It started, of course, as an undergrad biology, kind of pre-med, but still not quite sure about becoming a physician researcher, had a lot of ideas, but there's just the practical elements of life and the struggles and challenges along the way. But ultimately, I got accepted into a very robust program at Texas A&M College of Medicine, and they gave me the latitude to study cardiovascular disease, but I wanted to apply exercise as a therapeutic modality. So they had an investigator on faculty come in about my second year of my PhD, which you spend, like most people, your first couple of years are very didactic learning, still advanced classes and learning a lot of interesting stuff because we were doing essentially a very similar curriculum to the medical students. So it was real immersive. In that program, the research was looking at coronary artery occlusion in a porcine model, in a pig, so a large animal. That investigator, Dr. Janet Parker, had a very translational model, so I was excited about that. I always wanted to understand how my research work would apply in the clinical domain. And so that was a really nice space to work in. I was doing that, and it was really exciting work, and still I'm very passionate about the discipline of the cardiovascular work. But one of my committee members at the time was where I was actually executing my science. So he had a specialized capability where we could study microvessels, vessels that are smaller than 500 microns in diameter, and really understand the microvasculature of the body, and in my case, particularly the heart, and how it remodels and responds to, hypoxia or other kinds of stress and clots. But the technique also was applied to many different, particularly animal models. And one of the ones that his lab specialized in was rodents and exercise, but in a very particular case, the idea of rodents in mimicking spaceflight, which is hind limb unloading, when they take the animal and raise it up onto its 4 feet, so its back end is offloaded, doesn't receive, any kind of loading. So you start to have a similar effect to microgravity, but all models are imperfect. But I was watching this work go on and understanding kind of what they were studying, plus some of his collaborators were looking at bone blood flow, people were looking at muscular changes. So now I started to think about, aerospace applications for the work I was doing. Ultimately, his name was Dr. Mike Delp. He got a NASA grant. And when I finished my PhD and became a postdoc, I stayed around for a little while doing some molecular work. He asked me to lead his lab at Kennedy Space Center when he had his experiment. Now, this was the end of 2002, beginning of 2003 was the mission. So I was at Kennedy. We were standing up his lab, building the hardware and preparing for the mission. And that happened to be the Columbia 107 mission that did not return. It was, critically damaged during reentry, and we lost the crew somewhere over Texas and did not make it back to Florida. So very quickly, I learned a lot about the NASA culture, not just the research side, but how you respond to a catastrophic failure of the mission and loss of the crew. And that was the second major shuttle loss, the first one being the Challenger accident in the 80s. So at that point, experiencing all of that, and inevitably you're part of the investigation in terms of, at a minimum, you have to be interviewed, and they would try to understand, what did the laboratory have on board? Not only could it have potentially been a cause, but also were you receiving data that they could use to inform, like accident reconstruction? Were you telemetering data or collecting data that could be informative about the vehicle? So very quickly got to know NASA people, NASA scientists, and started asking about career paths in that world because I didn't really see the connection for me as a physiologist and what I was doing. But they did have some openings at Johnson Space Center, which wasn't too far away. It was just a couple hours away from where I was doing my postdoc. And I went down and interviewed and got a job with one of the contractors. And I began working in medical operations, supporting the flight surgeons. Because of my work in cardiovascular disease, that was one of their major concerns. Can the stressors of spaceflight maybe induce and or accelerate a pathological process like coronary artery disease? And as the astronaut corps naturally ages over time and they start to accumulate comorbidities, as much as they can get amazing healthcare, it's kind of an inevitability of our biology sometimes. And And then it became a question of how do we do better preventive medicine? How do we apply tools that were being discovered and, coming out into the healthcare domain? Or how could we apply tools that are very new and maybe used in other disciplines? And of course, one of the major capabilities we have in spaceflight to diagnose people is ultrasound. So, and at that point, you're talking, early 2000s, ultrasound was not doing what we were, what
Right.
NASA was asking it to do. So that's where you start to see this intersection of people who work at NASA and, develop research plans, or in my case, translational research activities. you know, we use funding of grants and contracts to push the edge on capabilities that are out there. We call them commercial off the shelf and to apply them. So I learned a lot about not only studying healthy people and emerging disease,
Hmm.
also the occupational health implications of going into a hazardous environment and characterizing the hazards of that environment, but then also working the end of the business case and the policy issues associated with your employees also being your test subjects, how you manage that. And sometimes there's conflicts of interest that you have to navigate through and conversations. But you also have to answer to program managers. And program managers, of course, usually are not discipline experts. In NASA, oftentimes they have been engineers, but they're not usually coming with a strong life science background. So you have to be able to articulate yourself and explain pretty quickly why the issue you're bringing to them matters and why should they invest in whatever it is you're asking for. Like, what's the value back to the mission? And I use this, it's a true experience of mine, but I use it to make people sensitized to the kinds of constraints. I think most people just can't comprehend the limitations when you go to space, but when you're at a table from, representing the human system and you're wanting to fly say a new piece of hardware to do surveillance or diagnose people or even treat people in space so that they can stay up there and stay safe and healthy and functional, you will be asked, how much food and water do you not want to bring? So the choices that really makes it vivid, right? About
Uh-huh.
if you're going to choose to bring something else, you got to
Hmm.
choose within your own system what you don't want to bring. What can you sacrifice?
Hmm.
Now, ultimately, there's other systems at play. There's environmental control and life support, guidance navigation, there's the physical vehicle itself. So there is other avenues to get more space, more mass, power, or volume, but that means you're taking it away from another system. So in your work, you have to start to really understand systems engineering and
Hmm.
how the human system, when put into this environment, becomes part of the systems engineering calculation. How can we quantify and objectify the data coming from the human and to enable the human to be not only healthy, but performance ready?
Right.
Because as you know, like even yourself on any given day, you can be
Hmm.
healthy, but
Hmm.
are you capable of performing whatever that means? Like with students, we often talk about, taking standardized tests and why you should
Hmm.
try to get a good night's sleep and eat a good breakfast.
Yeah.
But given the stress of the testing, maybe you don't
Uh-huh.
sleep so well and your stomach isn't ready for food. So the idea is under imperfect conditions, you still
Hmm.
have to perform. But we also have to realize like you cannot continue on a day-to-day basis, deprive people of necessary things because then you start to decrement their resilience. Like maybe they'll be ready the first couple days or week, but will that be true in 2 weeks or 3 weeks? And now we're talking about missions that are months and years long. So
Yeah.
my work at NASA, when it transitioned from medical operations, which was about 12 years, I moved over to a leadership position in the NASA Human Research Program, which is dedicated to understanding the human and addressing all of the human system risks that we can identify. And that was a job that crossed many disciplines. Like, no longer am I an expert in anything. I have many
Uh-huh.
experts I lean on. And that was an exciting opportunity and very intense,
Right. Yeah.
to try to feel like I had enough information and to make a decision and help scientists who worked with me to navigate these challenges of not only doing what was best for their own systems that they were worried about,
Hmm.
but across the whole, were we making progress with the countermeasures, which are the solutions we might bring? But we also have to look at before the mission, how we get them ready. And then
Hmm.
after the mission, how we help them recover and still have very long, healthy lives because they may refly again.
Yeah.
And they also want to go on potentially to other careers and have robust lives outside of NASA.
Yeah.
So that's kind of my arc through NASA. And now I've segued into academia to continue research, but on the other side.
Wow, that's really like wonderful, like all the experiences you've had, and you weren't in just one exact field. You got so much exposure over the years. To go a little bit deeper, could you tell us about one of the main problems you're researching right now or what you've seen in the field that you're in?
Yeah, so my position now at University of Central Florida, I'm a chief scientist for the Center for Aerospace and Extreme Environments Medicine, which is dedicated to multidisciplinary, interdisciplinary work, because that's really how we're going to solve these big challenges, right? It isn't going back to the constraints I talked about with, you have to trade what you want to bring and leave water
Right.
and food behind. They're all critical, right? Like taking less of one of them is a problem. So you have to start to think of your solutions in a multidisciplinary way. So I'll give you an example, and these are kind of archetypes and they're being worked on. And they also try to be bio-inspired by how Earth accomplishes the solution, but we realize we can't take Earth with us. So you also have to economize and be like the epitome of off the grid living and complete recycling. So there's a lot of pressures that on Earth we have them, but we kind of have luxurious circumstances. But there are places on Earth that don't have things, right? Like austere wilderness, native population, third world countries where we could deploy stuff, but there's some not good reasons why we can't translate the solutions. But in spaceflight, we have to solve the problem. Like if we're going to do the mission and we're going to be ethical and we're going to manage risk, we have to come up with a solution. They may not be perfect. We call it good enough, which is still pretty good. So what I think is important to say is the most biggest challenge is working in a bioregenerative environment. So we live in a very mechanochemical environment in the current spacecraft that are built. And they are built in the very literal sense of a vehicle, right? This sense of kind of how we design automobiles or airplanes. That is what we lean on heavily. And that is often like heritage hardware. We know they're safe, we know they're reliable, so we reuse it. But it doesn't necessarily get us in the space of the solution we really need for something like the Mars,
Hmm.
which, because of the mechanical nature of the solutions, they require repair, they require replacement. And you're in a situation where they themselves are, maybe in the case of environmental control and life support, providing the air and removing the carbon dioxide and managing the humidity. But they themselves are a resource consuming thing, meaning they
Right.
need some raw materials, they may need chemicals renewed. And so you're taking other stuff to make that system work. So going back to if every system were to come in with a single point solution for every problem, we wouldn't fly. So now you have to start to think of, well, what are the commonalities in terms of the needs and or the the thing the body may generate? Like if we exhale CO2 and it's
Hmm.
our waste product, what is CO2 a raw material for? Just like how we think of methane, like, well,
Yeah.
I could use methane to make water and hydrogen. If you can move the waste product from one place as a raw material for another, that's the kind of thinking you have to create. Essentially, I start calling the future vehicles really exoplanets, right? You have to have that
Yeah.
sense of you're not necessarily recreating Earth, but you have
Hmm.
to create the ultimate inefficiency of recycling, meaning my waste is something else's energy, right?
Hmm.
It's, the law. We
Yeah.
cannot create nor destroy, but we can transform it. So how do we do that? So in
Hmm.
the case of environmental control and life support, a living thing can produce oxygen, plants and microbes, and we can engineer things to be more efficient at producing oxygen and consuming CO2. Those same things, if they're plants or even some people are like trying to make goo out of microbes and yeast, but
Uh-huh.
palatability will come in. Some of the details make it a hard solution to really make practical. But the idea of plants could be consumed, they have caloric
Hmm.
nutrients, they've got micronutrients, they've got fiber, they got things that can help our microbiome, which is also at risk in a closed
Yeah.
environment. So we realize like plants are a thing we need to bring, but they're also vulnerable. Like, what if the
Hmm.
plants get a fungus and die and the whole crop goes down? So people on Earth are working on these things, particularly with respect to climate change and the way we've kind of engineered agriculture, particularly in the United States, that where does it make us robust? Where does it make us vulnerable?
Hmm.
And where have we kind of dismissed the idea of diversity? Because
Right.
diversity gives you kind of a backup solution.
Yeah.
So this idea of bioregenerative ecologists to me has been one of the archetypes of a multidisciplinary effort to create this future vehicle system that has a strong living component, not just the human living in it, but the actual vehicle environment having a living element to it to meet the needs of the entire mission.
Hmm.
But to be honest, like my work specifically, I help people who do bioregenerative work and I weigh in on the human component of it and, what we might contribute with respect to CO2 and why, but also how we consume food and use it for energy. But one of the areas when it comes to surveilling the human to know how well they are and if they should do something more of like preventive medicine is in situ analysis. So this idea of us, like if you go to the doctor and you get a blood sample and a urine sample, that sample goes to a big lab. And usually a lot of wet lab chemistry happens. There's lots of reagents, most of which are toxic. And they're very complex processes to produce the result that your clinician would look at and say, they're looking at mgs per deciliter or some unit when that biomarker comes back. And then we can someday discuss the upper and lower limit of normal, like how well have we really described the range of human normal
Hmm.
and what normal is for someone. But in this case, bringing wet lab chemistry on a space flight is not practical, right? For a
Right.
couple of reasons. But again, like describing, it's more reagents and more stuff to bring for its own purpose. When you're like, well, what else could we use to see the same molecules? So I've been on this mission to look at alternative methods that are typically brought on spacecraft, but not used on humans, which is like spectroscopy or human samples. Right. So you have a variety of spectroscopy capabilities that are really elegant and unique. They just weren't used and built in a way that they deliver results that, say, physicians and healthcare people are used to seeing.
Hmm.
But it doesn't mean we can't do it. So this is more of a technical translational job where I want to take existing capabilities that aren't traditionally used for an approach and start to understand if we can repurpose it because we could bring mass spec or Raman spec and it
Uh-huh.
could be used by the physics people, it could be used by the engineering people, it can be used by the doctors and the healthcare workers. So we can bring one and it can have high value because it's
Hmm.
servicing many needs. It's just that for Earth purposes, that's not been the tool that we've used and the tool we're comfortable with. So rethinking about how we solve some of these problems are really challenging because it just doesn't have the history of it. And people will say there's not a market for that because we
Yeah.
have a way of doing it. And my comment back is, well, we don't have a market for it because people don't know it's possible, right? No one's shown you the alternative to say you didn't want it or it wasn't viable, meaning it could be more efficient in terms of producing results and having less cost and less waste because it's not using toxic reagents. So I think we have the opportunity, spaceflight is a forcing function to rethink how we use tools of today that are less damaging to the environment and less hungry for reagents and raw materials that are problematic, and then get the benefit of having a tool that multiple disciplines use and could benefit from. So that is part of what we're going to be doing at UCF, but also even expanding that into wearables where maybe we don't have to take blood and urine from people. Maybe we can get these insights, and this has been in development for a while, but again, it's been a
Yeah.
lot about single point solution like using near infrared or photoplethysmography. Like what can we do with video? But then the question becomes a lot of times what we can do with video and lighting is good on one skin color, but not another. Right. So the challenges are still there and need to be solved. And we could ultimately have a really beneficial solution. And I think spaceflight asks really hard questions and forces a solution to be developed. And then how do we bring it back to Earth so we can deploy these things to people who have never had the capabilities before?
So you're saying implementing it is an issue? Like whatever you find in space, deploying it would be an issue.
Yeah, for sure. Like the constraints going back to the food or water, like there's limited power, limited data capability. It's usually like a right now they are working on the Deep Space Network, don't get me wrong. So there may be different opportunities to change what you do because the constraints may be lessened over time. But for the model for the near future, we have to build within a certain framework and knowing that those constraints forces us to build a much more efficient approach. We may get some latitude later to back off on that, like have more power or have more hardware. But right, the constraints are significant and the cost to fly to the moon, just getting off of Earth and the constraints about the volume For the human system, there's also a time element, meaning that when people talk, resupply can happen, but not very quickly.
Yeah.
So in low Earth orbit, the biggest risk is the rocket blowing up often when they're going to send resupply. Like we lose more of those rockets and the cargo that way. But
Yeah.
within days and hours, you can get a resupply. We've done that for emergencies before, like to get hardware up. This infrastructure concept of, well, there has been a launch queue. And what happens is we tend to take advantage of the very next planned launch. We don't push a complete contingency launch for the reasons I said. They tend to be more riskier. So it's great that you have this infrastructure for low Earth orbit. When people start building this moon base, there's no infrastructure. Not only is there no infrastructure on the moon to leverage, there's very little robust infrastructure to get rockets launched again. And the facts of it were recently, just weeks ago, we lost a Blue Origin rocket during a static test fire here
Mm-hmm.
at Kennedy Space Center. And that was Blue Origin's only what's called heavy, meaning the largest rocket they have,
Mm-hmm.
launch pad, because they were still in a testing phase. They're not operational. And these
Mm-hmm.
launch pads are difficult to make because they have to be safe in the infrastructure and they're trying to protect the environment. It has a lot of requirements on it. So
Yeah.
people aren't building 3, 4, and 5, launch capabilities. They're
Mm-hmm.
building one, and this one happened to be heavily damaged. So it will take a while to replace. So
Yeah.
in this model, if we've got a lunar base going with people on it
Mm-hmm.
and we lose a rocket with resupply and it takes
Yeah.
out the launch pad, well, they don't get resupply for 2 years. And this was actually what went on after we lost Columbia
Mm-hmm.
because they suspended flying the shuttle program until they had the accident investigation. And so
Right.
we could not send shuttles up to the International Space Station. We were constrained to the Russian capability with the Soyuz, which has been very robust, but
Mm-hmm.
it wasn't geared up to do double the work or triple the work when
Yeah.
shuttle went down, instantaneously. So we saw 2 years of International Space Station that was pretty lean. Like people weren't getting fresh food. The group that was up there when we lost Columbia, they were at risk for running out of food. Then you're starting to make deals with another country to fly
Mm-hmm.
food for you and have to get food over there, which means they're not going to fly something else. They may not fly hardware. Well, if the toilet breaks and they took the toilet parts off because they
Mm-hmm.
had to put food on, well,
Mm-hmm.
now what do you do with a broken toilet until you can get the next vehicle up? So the practicality of what goes on in spaceflight, it's just at a premium because you don't have Amazon delivering it.
Right.
Not overnight, not same day.
Oh.
It's called Blue
Mm-hmm.
Origin, and it's called SpaceX, and it's called Vast, and it's called Axiom.
Yeah.
They're working on it, but inevitably, when you hear these things, like when Blue Origin lost their vehicle, it is hard, right? These
Mm-hmm.
are risky
Definitely.
things because there's a lot of volatility to the event.
Mm-hmm.
So no one should overly criticize and cast aspersions. It's
Yeah.
also how we learn. And it's the ideal case that if you're going to learn, you're going to learn on a launch that did not have humans on it, right?
Okay.
So this
Mm-hmm.
is why it gets very, for those of us in the industry, very nerve-wracking. Like when Artemis II went up, the first launch of that rocket with that capsule with people on it,
Mm-hmm.
because the one before, we had a successful Artemis 1 that didn't have humans on it, but that vehicle came back and had trouble with the heat shield. And
Yeah.
that kind of reflexively brings up Columbia because
Mm-hmm.
of and it got damaged. And so for those of us who have that memory and have actually been part of the lived experience, you're like, it's never a certainty that those rocket
Yeah.
launches and returns will go well. So we kind of, I think, internalize that precision, resilience, robustness criteria in a way that people who don't work in the industry would have a hard time appreciating. There are other dangerous industries on Earth, so like mining and aviation. There's
Mm-hmm.
reasons why those industries also have a high degree of risk reduction and precision that may make things slower and may make things more expensive. Because when we don't do those things, the accidents are catastrophic and have a lot of collateral
Yeah.
damage.
Going on to Artemis II, I saw that you were part of the launch coverage. So could you tell us about your role in the mission and the launch?
So I was launch coverage for a local Orlando station. It was really an exciting opportunity. You're very passionate about something and you want people to really appreciate the magnitude of what's happening. And it wasn't lost on us that in Orlando and Kennedy Space Center, and having come from Houston, those are communities who are well educated and knowledgeable and have it in their backyard. But this was an opportunity to talk to a much larger population about what was going on with the launch. And I felt very honored, to have a voice in the launch activities and be there and get asked really good questions about what's
Hmm.
going on and what did I see and what did I value and what did I think was really exciting about Artemis II. That was such a milestone, not just because it was from the United States. I mean, I felt that was a little overemphasized. Like, it was still an international endeavor. I mean, like, there are so many people involved and so much history there with so many countries and brilliant people from around the world who have contributed to this technology and this capability. But the mere fact that we were getting humans so deep into space
Right.
to reestablish that capability and also represent themselves as humans out there having this honor of going and making the most of it. Like, you're our eyes and ears as you go out there. And they did such a beautiful job of communicating that back to us here on Earth and also doing science, right? It wasn't just about operating the machine so we could be there. It was about using that opportunity to understand what was going on in our universe, what is going on with the planetary body of the moon, mapping the backside of the moon and where might we go next to really understand how we can use the moon as a learning opportunity and also respect its existence. I mean, I think the other thing I hear a lot about is people wanting to go there and do very industrial activities, more or less mining the moon. And I'm like, well, I think we need to also take a moment to understand just because we can doesn't mean we should. Like,
Yeah.
how is this ethically going to be discussed at the highest levels in the globe? And
Hmm.
we do have some treaties that exist. There's different responses about the Outer Space Treaty. It's like of 1964, but nevertheless, I think it's worth rediscussing what are our intentions when we go and
Hmm.
what are our intentions to share what we learn so that not everybody has to go to do that thing over and over again. I
Yeah.
think that's a real challenge that we've had in terms of what I've seen individual countries like want to put out there. And I was like, this should be way more collaborative than competitive.
Exactly.
And I think we could learn more together. They always say, like, if you want to go fast, go alone. If you want to go far, to go together.
Hmm.
And this is really the safest way that we can build the capability to do a Mars mission
Hmm.
by having the backup of both low Earth orbit and Earth not too
Yeah.
far away to manage the situation when we needed to do a learning. And learning includes failing. Like, the idea of failing safely means you had a plan B and
Exactly.
there will be minimal collateral damage when you're learning your
Hmm.
lesson.
Yeah. Leading into my next question, so as we move from Artemis II towards longer lunar missions or just Mars, as you mentioned, what advances in aerospace medicine or in your field do you think are crucial over the next decade?
Yeah, definitely the element of autonomy, meaning you're going to be sending a relatively small crew for the foreseeable future, 4, maybe 6 people. Like, there's even much debate about, the necessary number. Like, is there a minimum and a maximum, like, not only from the psychosocial standpoint, but it tends to be the volume of the vehicle will determine how many people can go. We have limits about habitable volume and people successfully living in certain enclosed spaces. But it's also, we always ask when we're in these mission planning activities, what do people expect of the humans? What do you want them to do? Right? We can help them be capable of almost anything, and we could tell you how we need to take care of them and them of themselves, between their nutrition, their exercise, their mental health. All those pieces have to be addressed, and we can, again, objectively quantify many of those pieces to give the mission planners and the designers of the vehicle the needs of the human. And we call them requirements. Often they want them synthesized down to a single number. And we're like, rarely when you're talking about the human population are you going to get a single number. But we can give you a reasonable range on how to, again, have some agility in the system with how we implement things. We only need one of them, but we may implement it 4 different ways, unique to each crew member. The answer is it depends. So, but when it comes to medicine and like the idea of people becoming ill or injured, it's hard even for a physician on board. There's 2 layers, right? It is the physician who could become ill or injured.
Yeah. Yeah.
Right. So if that's the only brain on there that can execute and you're only one deep, like, that's a problem. So we don't do it that way. But the other element, even for that person, they never know it all, right? The expectation that they could know all and do all is just unrealistic for anyone as expert as you are. So they're going to need help. And when we talk about autonomy, this is where we start to get into, artificial intelligence, machine learning, augmented reality. And right now with low Earth orbit and even in the lunar state, you could use telemedicine where you can call back and we can have a room full of people. You call it like the back room. And
Yeah.
virtually, you can bring any expert from anywhere and we can tie them in, which has been beautiful. But pretty quickly outside lunar orbit, you're going to be losing that capability robustly. Like it just continues to diminish. And there's a point at which the communication lag is so disruptive, it's counterproductive. So you're going to have to learn how to embed capability on board and
Mm-hmm.
send it with the people. Now, what's beautiful and I think is under discussed, even when people are 40 minutes away from a comm loop, the Mars scenario, we can continue to update from Earth to them, kind of like with the bandwidth. Like you kind of trade off who gets the bandwidth when you're uploading and downloading data. And it would be the medical system architecture people that are on Earth or on the moon continue to evolve the procedures and the capabilities. And we would re-update the software so that it wasn't like it was just a software package and it's finite and we send them and they go. It's still a living thing. It just cannot be effective real time. So we have to work on that because a lot of the limitations are about the capabilities of AI and ML being accurate
Mm-hmm. Yeah.
and trustworthy. And that's how we train it. And some of this training will have to be unique. So, another element at Central Florida that we're doing in the College of Medicine is building a laboratory, a simulation capability where we can do a lot of that training and create artificial limitations that drive the same use case scenarios that we have in space to a high degree, not a microgravity room. No one's got one on Earth. Sorry. Um, no big secret there. But it'll have the other features. It'll be constrained, confined, isolated. We can mimic comm delays. We can remove hardware. We can add hardware simulating an emergency situation. We can fill it with smoke so you lose your visual capability. All those things where you actually take people who emulate astronauts, put them in there, and have them be trained, but say, when you go under these circumstances, where do you succeed and where you fail? How have the tools helped you? How have the tools not helped you?
Mm-hmm.
So we start testing them on the ground and refining them before we ever put them into a more higher fidelity analog like Antarctic or these expeditionary activities that mimic so much of the constraints that they really deliver the keen insights that are very applicable and translatable to spaceflight. But then low Earth orbit is its own analog, and so will the moon be an analog for the future.
So, final question. Many students, including myself, were inspired by careers in medicines and space exploration. What advice would you give to these students?
While your passion may be what starts you down in place, pretty quickly what you're going to identify is that there has to be something more sustainable than just being passionate about something. And I think that's when you start to identify how you're going to apply, like how are you going to give back? Like when I produce a thing, what I find is people who are wrapped up in publishing the papers and getting their name recognized and getting the award, like those are nice, but the feeling of it doesn't last very long. But when you see what you did have an impact on people's lives, that's like well beyond what an article you wrote could have ever done. And it's not that they even know I was involved, but when I see what's gone on with the application of ultrasound in emergency rooms and knowing I was a small part of that, like to push the limits on what we needed ultrasound to do and be part of the group that would write, the research announcements and be part of the selection group, that's one of those that told me like I actually want to be on the other side of that. And that's why I left NASA. I really enjoyed and I benefited, as you said, from every element of a diverse career within NASA itself. I had probably 10 different jobs over the years. Loved every one of them, learned an incredible amount about my own capabilities at times, what I was
Yeah.
really capable of. But at some point, like, no, I want to be in the field. I want to be on this side, sending NASA the stuff I think they need.
Mm-hmm.
But I also want to be in the field, bring it to the people who need it on Earth. I don't want them to have to wait any longer for someone else to figure out it should come back to Earth.
Yeah.
I want to be part of the team that actually does the translation and commercializes things and helps them understand that there's a market because people would benefit from it. So that has been kind of my long-term like guiding light. Overall, I'm very passionate about it, but the reality of seeing it applied and knowing I could do more to apply it for people who don't have access to healthcare today and
Yeah.
get them capability, that's really what keeps me going every day.
Wow, that's really meaningful. And I'll try to stick with that too, not just about the passion, but what you want to do for other people as well. Thank you so much, Dr. Fogarty. Thank you so much for joining me. And it was truly a pleasure learning about your perspective, your experiences, and the advice you had. And thank you everyone for watching. If you enjoyed today's conversation, be sure to follow along and see you in the next one.
Thank you.